this computer. As a matter of fact, let me mention one thing about it that I meant to mention yesterday, but just as a reminder, on the test review, I went over that kind of at the end of class. All right, I'll turn my music off. I went over that at the end of class yesterday, but just want to highlight, I'm definitely going to ask you a question about making a Laplace transform. One of the simple ones, not that. I won't ask one like that, or like that, or like this. I'm not going to ask some of these cool dodges, but what were the simple ones? Well, the ones I have circled on the left were simpler. And then I guess these Laplace transforms of derivatives, those are pretty important. We've been using that a lot. Like those are possibilities. So I want you to be able to produce that. And then we'll get back to this later today. After I kind of get you rolling on the project, then we can kind of break up and talk about whatever you want. I can set up, breakout rooms. We can go talk one-on-one about something if you want. But you can ask me to do one of these questions. But the main thing I guess I'll just quickly repeat is you're going to be doing everything on this test with Laplace transforms, and you can certainly check your work as per usual. But notice there's kind of every example here. There is a second order equal to E, a second order equal to trig, and a second order equal to a polynomial. So being able to take the Laplace transform of both sides and decompose the disaster that's left behind to produce your answer. And as I kind of warned you yesterday and tried to model the last couple of days, like do your work really organized so that if you do make a mistake, because these are such long processes, you're probably going to, that I can give you lots of partial credit for that. And I will say, especially if you tell me, if you go check it using maybe Desmos and tell me your answer isn't right, but you can't figure out why, all the better, because you only have so much time to take the test. So of course you're gonna, if you did make a mistake, of course you're not going to be able to find it. So the project, which is not due till, I want to say it was Wednesday. Yeah, it's not due till Wednesday next week. So you have plenty of time. Really, I'm introducing this today and I'm sort of expecting you won't do anything with it, and because you'll kind of, I don't know, be studying this / getting ready for the test on Monday. You could wait till after the test and just study the test the whole time if you feel like you need to. But this is just an absolutely wonderful problem. And it deals with this cool curve called a catenary, or as the British have it, a catenary. And it turns out that there is a whole bunch of really interesting history about this shape because, and I'm going to show you a quick video about this in a second, but when you hang a string or a cable or rope or whatever between a couple of points like this chain right here, it hangs in the shape of a curve. And it was a tremendous mystery to early mathematicians and scientists as to what that shape was. Is it a parabola? Is it a circle? We had this conversation before about the bending of a beam, or maybe it's the same as the beam. Remember how the beam was actually a 4th degree polynomial? That's actually a chunk of a 4th degree polynomial. Well, what is this thing? What is that? Is that a new curve, or is it one of the ones we already know? Well, it turns out it's none of the above. It's a brand new curve you've never seen before called a catenary. And it just has I've spent uncountable hours with this concept just because I find it so interesting. I did a talk at a math conference a few years ago about zip lines, just because that's sort of the fun consideration of this. Again, my philosophy is, if you see a chain like that and you nerd out on the sidewalk, that's not near as interesting as somebody who says, I've got this tree over here. I don't know if you've ever done the zip lines out in Gold Hill, but they're actually pretty awesome. But, it's like I'm going to hang this cable from this tree and it's going to curve down and, land over here against this other tree that's, way downhill or whatever. So the idea that, somebody's got to go first, and what you don't want to do is swing all the way down to here and come to a stop. That wouldn't be good. Like you didn't have enough fall. And what you don't want to do is get on here and be going so fast that when you hit that tree down there, you're still going 30 miles an hour and you bust up your person. So, I spent a whole bunch of time like doing the math on how do you design that? How do you come up with that? Well, it turns out that shape's a catenary. And so it's a really complicated mathematical shape. It's a brand new curve that you don't know about. And on this sheet, I'm actually telling you what their equations are. The project is ultimately, can you derive those? Notice the top one is got that H in it, which means hyperbolic cosine. It's a brand new function related to cosine, but not cosine. And that's on your Laplace transform sheet. And so if you solve this problem using a Laplace transform, you may remember yesterday I pointed out the only difference between cosine and hyperbolic cosine was that little minus sign with the b squared. You'll get the equation arc hyperbolic cosine. I'm sorry, that's not arc, that's an A in front of it. If you don't, then you'll just get something, well, you do recognize. Notice that other one is just e's and so forth. So let's take a second and just look at that second one, A over 2. And this project is up. You might want to pull it up, but I'm going to share a different screen now. And show you what this shape actually is. Again, this is kind of interesting because I'm actually asking you to reverse engineer this. So this is the equation I just showed you, at least the one you recognize. You don't understand necessarily hyperbolic cosine, but you do understand E. So if I say E raised to the, and I'm going to say it a little bit differently, 1 over A times X. The way I wrote it in the sheet is actually better, but just that you would see that A is just some number. So if A was 2, that'd be E to the 1/2 X. And then you get an exact repeat of that, except for, interestingly, it's just a negative sign. So I hop out of there, throw in a plus sign, bam, repeat myself, except for now I throw a negative in front of that. And so what I want you to stare at here is that A coefficient, or yeah, I guess you could say it's a coefficient, that A constant. What does that have to do with the graph? Bam, there it turns out is the equation. So it turned out it wasn't a parabola. It wasn't a fourth degree polynomial. It wasn't a circle. It's none of the curves that we recognized before. And by the way, if you get interested in this and want some extra credit, go search up the history on that. Who figured it out? Who figured it out with something else? And then, how did they figure it out? Because it turns out it's really close to a parabola. But maybe you've stared at enough parabolas that you can tell that's not one. Can you tell it looks a little too flattish at the bottom?
Okay, I would go to my death to say that's a parabola, I'm telling you. If someone tried to tell me that wasn't a parabola back in the day, I'd have started a war for sure.
Liar, you would have burned him at the stake, wouldn't you?
Yeah, I mean, I just don't see it.
She's a witch. But watch this, here's proof. I just made a parabola that goes at the same spot, but notice it isn't quite a parabola.
All right, Desmos would have prevented the war.
See, now that guy doesn't have to burn as a witch. It saved him from Connor.
Too little, too late, Doug.
They're already dead. Well, that red curve, the catenary, is a little sort of flatter at the bottom. That's kind of what I meant by that. And so you can appreciate that without much technology, for those people to kind of prove it wasn't a parabola was rather difficult. I think it's sort of obvious it isn't a circle, maybe. But what I want you to stare at for a second is like, what does that A seem to be doing? Can you find A on, this is not a trick question, it is very easy. Can you find A on the graph?
Yes, it's the y-intercept.
Thank you. I know you don't like to state the obvious when I ask questions sometimes. I get that. But yeah, that's exactly right. It turns out that A value, and I think I said this on my sheet, that actually is the y-intercept. And of course, that's kind of weird, right? Because it isn't like down here where I said +1, I put +1 and that made +1 the y-intercept for the parabola. So notice this didn't just say plus a. So it's kind of weird that that a is actually the y-intercept of this, but it turns out that's the equation of a catenary curve. And because that hangs entirely due to gravity, does it make sense if you took that shape and you flipped it upside down? That would actually be the best design for a bridge, because that is kind of spreading the weight evenly. So let me see. I'm not sure. Seems like if you just make this negative, then that flips it upside down, doesn't it? So if you made a bridge like the Gold Hill Bridge, you made an arch bridge, something of that nature, that turns out to be the best shape you could possibly use. Now, again, it's pretty indistinguishable from a parabola in terms of the practical handling of it. But what this shape does so cool is it actually evens out the tension. So if I take you back for a second, well, if I take, I'm not going to go back there, I don't think, but if I remind you of that chain that I showed you a second ago on your sheet, each link under that chain is actually feeling the same pressure. That's kind of what happens. And if you imagine not just a chain, but like a bunch of people, say, holding hands and being stretched up in the air, if you were strong enough to hold yourself, what that cable is doing is equalizing the pressure between all of them, like nobody's working any harder than the other. And so when that shape equalizes its pressure like that, this is the shape that it takes. And so, you know, of course, you can appreciate, and that's what this project is about. You can appreciate the goal here is to try to figure out, well, what curve would that be? And so before I kind of show you the math behind some of what's on the sheet, I want to let you watch this quick, pretty good video from a Brit. And I think they call it, I've watched this video forever, but I think they do call it in here the catenary. So this dude calls himself the singing banana. I don't know what to make of that, but
I can't hear it.
you can't hear it.
Yeah, me neither.
You guys can't hear that at all?
I
wonder
don't
if-
know if Zoom shares audio. I don't know.
It could
I
be.
think there's a way to do it, but
Yeah, it should share audio.
yeah.
Clicking around right now. I guess I've never had an occasion to do this before. So share sound. Let's try it again. I just hit share sound. I found that button.
It forms a curve
That works.
There you go.
called a catenary curve, and it is not a parabola. It is its
Hear
own
that,
type
Connor?
of curve with its own type of mathematical.
Oh, I hear he's looking a little suspicious. I don't know.
He's a
See,
Brit.
back in
He's
the day, he'd have had to hold that. And he'd be like, "Look, this isn't a parabola." I'd be like, "Look, I'm
Catenary is
gonna fight you. I'm
derived from
sorry."
Latin for chain because it's the shape formed from any chain or rope hanging freely under its own weight. And you'll see this simple and beautiful piece of mathematics everywhere, from the wires in an overhead power line to the strands of a spider's web. But why do we see this curve appearing again and again in the natural world? To answer that question, we're going to turn to the world of bubbles. To
Bubbles.
minimize their surface tension, bubbles form perfect spheres. If we try to form a bubble between two rings, it cannot make a sphere, so instead makes a curved shape. This time, to minimize its surface tension, it makes the catenary. So a chain, like in the world of bubbles, wants to minimize its tension, so forms the catenary, and it is not a parabola. The parabola is the arc of a ball flying through the air. Its mathematical description is y equals ax squared plus bx plus c. By eye alone, it looks like a catenary. Galileo realized that the curve of a free hanging chain was very similar to a parabola, but something was amiss. The mathematical description of a catenary is actually quite different. It is y equals a cosh x over a. That's equal to a over 2 outside of e to the power x over a plus e to the power minus x over a. The curve changes as the distance between the two ends and the length of the chain changes, but they can be described with the same formula and are never parabolas. Man uses this natural form in the worlds of engineering and architecture. For example, the wires of a suspension bridge are parabolic due to the weight of the bridge it carries. But without this weight, it is more like a simple rope bridge carrying the same weight along its length and will again be a catenary curve. But if the catenary is the shape of a rope or a chain that minimizes forces in tension, then by turning this upside down, we form an arch which minimizes the forces in compression. And it's actually the strongest kind of arch, strong enough to support its own weight. For example, that's what the master builders of the Middle Ages did to construct this, the ceiling of King's College Chapel in Cambridge. So to make the strongest kind of arch, you can simply mark out the shape of a free hanging chain and turn that shape upside down. So now that you know what a catenary curve is, you'll be able to spot it everywhere. So next time you see an archway, a bridge, or a spider's web, remember, you're seeing mathematics.
There you go, as the Brits have it. So I think he said, like I said, I haven't listened to this for a while, but I think he said that the word catenary is the Latin word for chain, catenary.
So this is the day that parabolas became obsolete.
Yeah, parabolas are like, that's for simpletons.
Engineering doesn't use parabolas anymore.
I don't know if you caught this, but it's pretty interesting because I've spent a whole bunch of time on this concept too, but just to try to make sense of it. But he mentioned that the cable for a suspension bridge, because of the weight of the road pulling down on it, actually is in the shape of a parabola. But without the road pulling down on it, just the cable's own weight before you put the road on it, it actually hangs in a catenary, which is rather fascinating. And it turns out to be true. It took me a long time to understand that well enough to be able to repeat it. Now, so as I've said, my ultimate goal teaching you math is to ruin your life. When you go around, after you investigate this and understand it, because your interaction with this is going to be a lot deeper than that video. And I think the average person could watch that video and go, oh, that's kind of interesting, but they're not really going to care. And I get that. It's like, yeah, whatever, it hangs in that mathematical curve. And so whatever, move on. But what I want is for you to build, like he just repeated those two equations that I gave you on my sheet. But what I'd like to do now is give you a little bit of background, just because it's kind of cool to do so behind this, because the project really comes here. The catenary curve turns out to be a solution to this differential equation right here. This also illustrates what I've tried to get across, and again, outside of kind of the normal boring book problems, the fact that differential equations exist in the world, and sometimes it's the only access you have to a problem. And so, he intimated that Galileo kind of saw there was a problem, like this thing is not a parabola, what is this thing? And didn't really say whether he solved it, which is what my extra credit was about, or whether somebody else figured it out. But this circled equation that I gave you here is the only access we have to this curve. So it's like, what's going on? How do we figure this out? And so here's the equation that you get. Well, from your perspective, you should say, hey, look, a second order differential equation. I'm not so unfamiliar with those. In the last month and a half, actually not so much afraid of that anymore. The question is, can you turn that into these? Project, can you go from here to here? Can you solve that second order differential equation? Now, this is very much outside the box. I'm not going to give you any hints about this. So I want you to talk to each other. I've had some students in the past come up with really novel ways to pull this off. But in the end, all the project is can you solve that differential equation? And again, the cool thing is there's your answer. Like, did you get one of those? Well, then you got it right. As per usual, I really would like you to get this. And if I need to give you hints, I am perfectly fine with that. Obviously, your sense of power as a human and as a mathematician is going to go up if you can kind of get it on your own. So that's certainly kind of worth your effort. I mean, I think to walk the street, and this is what I mean about ruining your life, you're with somebody you like and you're like, check this chain out, and you start explaining it to them, and then they want to get away from you, because your excitement of it is going to grow if you can actually kind of build this equation entirely for yourself. Now, what I want to take a few minutes to do is answer the question, where did this come from? Because again, you can Google search that. You can Google search that and find where, just find that someplace. And so notice it's sort of terrifying just to stare at it a little bit. Notice there's an A in it, and that's the same A we saw a minute ago. That A is the y-intercept, if you will. But notice it's got a second derivative and it's got a first derivative. But notice that first derivative is squared. That's rather alarming. And then, of course, there's a square root around it. Notice it has sort of a Pythagorean theorem kind of a look to it. And so I just want to, you don't need to know any of this, but for those of you that are interested, I just want to give you a second to kind of understand, where did that second order differential equation come from? And so here we go. And it takes a little bit of, I don't know if you want to call it physics or engineering to understand this, but let's do this. So we have this catenary. So here it is, this cable hanging here. Notice I purposely draw it kind of not even on both sides. And again, it's kind of fascinating just because this is even worse. But the problem I spent time playing with is, if that chain there was, say, 10 feet long, does it make sense you could hold it up high in this position and up low in that position, and then it would just hang where it's going to hang? Does that make sense? So if you actually knew where those 2 points were in space, and you knew how long the chain was, does it make sense you should be able to find the equation of that curve? That turns out to be really hard, even though we kind of say we know the equation. But then, of course, if you pull them further apart, does it make sense it's going to, be a flatter sort of a curve? And so, the question is, I have a 12-foot chain, and, where do I put my fingers? The most I could do is pull them 12 feet apart, in which case it'd be flat. But if I moved it in, like 6 inches, now it's 11'6". How much would it hang down? And you can appreciate, and there's some internet information on that, because you can appreciate people that run power lines have to think about that stuff, right? Like how much do I hang between these two poles, because I don't want it to hang down so low that somebody can reach it or hit it with the top of their car. But back to the matter at hand. So I'm going to go right to the bottom of this, kind of on the XY axis. And I'm going to go over here to just some random point, call it point P, and of course that's some point XY. And so I'm just looking at a chunk of the curve now. And we already decided, interestingly, that, and this is very important as far as your project goes, that if I put this on the axis right here, that point is at the point 0A, right? Because that's what we saw A was the y-intercept, so that's the point 0A. And so I only want to look at this chunk of the wire right here. So notice I fixed the left side at the bottom of the curve for sure, but the right side is still anywhere. Like I didn't say go to the 0.27, I said XY. So that could be, way down here at the bottom, or it could be way up here at the top. It can be anywhere. So here's what turns out to be true. There is a horizontal force here. You can appreciate if you cut the chain and you were holding it right there, you would have to pull with some horizontal force in that direction. In other words, you'd be being pulled on, right? If you were holding that end of the chain that we sort of pretend is broken now, the rest of the red stuff is gone, and we just have this little black chunk, you'd have to pull over there. And you'd have to pull over here. Notice this would be tangent to the curve. Actually, I think I want to change colors on that so that it doesn't. So I can't call this like vertical, but I'm just going to call it T for tension. So can you appreciate if that chain was going to hang there like that, you'd have to kind of pull on it in that way. So one person's kind of pulling in each direction. So H for horizontal, T for tension, tension pulling, doesn't matter what the letters are. And here's where it gets kind of interesting. Now, so depending on where you made that point and what your chain was made out of, does it make sense your little chunk would have some weight? So maybe it's 10 pounds. I'm going to write pounds in here only so that you understand that that's a force. So that, you know, that chunk of cable might weigh, notice I said W pounds because it depends what the cable is and it depends how long of a piece of it you have, but that would have some weight. And so it turns out this is the three forces that are acting on that weight or acting on that cable. Somebody would have to be pulling on each side of it, or at least that chunk would be experiencing a pull on each side of it, and then that weight would be pulling down. And so one of the principles of statics is that these forces would all have to balance. In other words, the vertical forces would have to balance. If they don't, then that cable would be flying up in the air, flying down to the ground. So why isn't this cup falling to the ground right now? Well, the cup has weight. It wants to go to the ground, but then my hand is there pushing back equally. You agree with that? If the cup weighed 5 pounds, then apparently my muscle is able to hold back 5 pounds because look, it isn't moving. So it's like our cable isn't moving. And so does it make sense that the chunk of T that's pushing up and the chunk of W that's pushing down would have to be a match because the chain's not going up or down? This is what the study of statics is about in engineering. And then there's also left and right. Well, notice W is not going left and right. It's only going down, so I can ignore W, but H is pulling left, and then a chunk of T is pulling right. And so all those have to match, otherwise that chain wouldn't be moving. And so if you look out at the street and you see this cable, as I'm looking at right now, and it's not moving, apparently all the forces of it are in balance. Again, you don't need to know this, it's just kind of cool. Okay. So how do we, well, kind of show that equilibrium? No force in X, no force in Y, it's all in equilibrium. How do we show that? Well, in order to break this thing down into its components, let's move this guy, point P over there. Do you agree that there's a chunk, there's the chunk of green that is going horizontal, and there's the chunk of green that is going vertical? So that makes a right triangle such a huge part of mathematics and physics. And so if I gave this angle right here a name, theta, notice I don't know what it is. I can't say that's 30 degrees or something. It's just, it depends where you are, right? If you're at a different spot, that's going to be a different angle. If this tension T right here, and really that tension T is a reference of the length of the green vector. So if that's T, then would you agree I could say the sine of theta is opposite over hypotenuse? And so this length over here would be T times the sine of theta. And in the same way, I could say the cosine of theta is adjacent over hypotenuse. And so this length over here would be T times the cosine of theta. And so for everything to be balanced, AKA not moving, or as we say in engineering, in equilibrium, would you agree that two things have to be true? One, H has to be equal to T cosine of theta. Do you see that in the picture? In other words, H is pulling left with say 40 pounds of force. Well, then T cosine of theta is the portion of T that's pulling right. Those would have to match each other. Again, think tug of war. If one side of the group pulls harder than the other side of the group, then the rope moves, right? Like if they pull equal, nobody moves. But they're both pulling, and if this thing isn't going to move, then those have to be equal. And wouldn't it also then be the case that W pulling down would have to equal T sine of theta pulling up? again, just to back up real quick, what are we doing? We're trying to build the second order differential equation. We're trying to build that. Where does that come from? Just because it's kind of fun to know. Again, you don't have to know it, but it's just kind of fun to understand it. Okay, so this is the backbone of this problem. And maybe you can get the feel of that, even if you haven't had statics or very much physics. Maybe you can kind of say, yeah, if that's not moving, then those forces would have to be in balance. I get that. Now let's start doing some really creative things.
The W could be anywhere between those 2 points, as long as it's going straight down, yeah?
That's right. It doesn't matter where that W is. There's nothing actually saying it'd be perfectly in the middle, by the way. But yeah, it actually doesn't matter where you draw it for this problem. It's just that it weighs something and it's going down.
Okay.
Doesn't matter if it's 4 inches to the left or the right. Good question. Okay. So let's do something weird. Let's take W and divide it by H. Well, that would be T sine of theta divided by T cosine of theta. But what do you notice about that right-hand side?
T's cancel.
The T's cancel. And then what's another way to write sine over cosine?
Tangent.
Tangent. So W over H is equal to tangent. That's kind of cool. Now, here's something interesting that I want to add to what we did earlier because of what we're about to do that is not obvious and kind of surprising. One of them is this W changes with P. You should agree with that. In other words, if I move P, then doesn't W change? Like it's not going to be the same weight. If you move X around, then of course W is going to get bigger or smaller. If I move it to the right, then W is going to get bigger because I got more chain, right? That doesn't seem terribly surprising. Turns out though, H does not change with P. If you move P, H actually stays the same. Again, I think that's kind of surprising. Hence, it's actually a constant. H is a constant. Now, why does that matter? Because I want to take the derivative of this thing.
Doug, is this anchored at 0A? Is that what H is?
Yeah.
Okay. Oh, just make sure.
H is the force pulling left that the person would experience if they, got rid of that chunk of the chain and then they stood there holding it instead. That's what that person would feel. And so oddly, and doesn't this feel not true? Oddly, if you're standing there holding it and then they went further up the cable, it sort of feels like, wouldn't that change? Like I'd be pulling differently, but the answer is no, it's actually the same. So H is a constant. That's important because we're about to take a derivative, and W being a variable and H being a constant is going to affect what happens to them when I take their derivatives. Does that make sense? So this is rather profound then. Do you agree that the tangent of theta is the slope? Like, isn't that what tangent of theta is? Tangent of theta, look back at our triangle over here. Is it tangent of theta? Rise over run. Tangent is opposite over adjacent. That's the slope, isn't it? Isn't that what we've done projects in my classes before on that? The tangent of theta is actually the slope, which is dy dx. So my second equation there, that's why I wrote it that way. Now let's take the derivative of that. And I'd like you to try that really quick. So take the derivative with respect to x. Can you take the derivative of that with respect to x, knowing that w is a variable and h is a constant? I'm looking at the chat. Ben's life is being ruined already. That makes me so happy. Thought it would at least take a week. So in my notes, I said, now find d dx. I mean, that's the way a mathematician would say that. I could have said just now take the derivative, but if you don't know what letter you're taking the derivative with respect to, that's not as much information. But if I said, let's find d dx, then it's find the derivative of this with respect to x. And so what would that become? Well, what's the derivative of w with respect to x? It is the derivative of w with respect to x. Like I can't take it. I don't even know what it is. It's just a, it's a, right now it's a number, but. And then isn't the h just come along for the ride? Because that really is kind of acting like 1 over h times w. It's like 1 over h is like 1/3 or 1/5. I mean, it's just a letter. And so what's the derivative of w? dw dx or w prime. But what's the derivative of the other side, my friends? Well, it's already a derivative.
It's going to be a second derivative.
Yeah, second derivative. And so we usually write that like this. We've talked about that a little bit.
Finally makes sense why we write it like that now, because you're multiplying it by that d over dx. So the d is squared, but the dx, the whole thing is squared.
That's right. And that's really because this d right here is kind of an operator. It's an operation.
Mm-hmm.
Like we're going to take the derivative once and then twice of y with dx both times. And so y is the 2 here and y is the 2 there. That's kind of the reason, because you're really taking the derivative twice. And then with respect to x, like you could think of that as having a parenthesis around it. So again, that's just sort of strange, but in the end, we're just going to take the derivative twice. Well, notice we're getting there, because like, isn't that what y double prime is d2y dx squared? I mean, that's what a second derivative is, right? That's just another way to write it. So maybe I'll just throw that in there, or y double prime. So we're kind of getting there. Cool. Well, let's fill in a bit more detail then. What about this? Let's add this knowledge to so the only problem we really have here is like, what is this dw dx thing? Like, what is it? I'm okay with h being a constant, because if somebody just told me, hey, that number is 100. Okay, fine. I stick 100 in there. Then I'm okay with dy dx squared, and I'm okay with 100. But like, what is this thing? I don't know what to do with that. You understand what I mean? So, well, would you agree that mathematically it would have to be equal to this? If you just do the algebra, so to speak. Okay, fine. So there's a couple of things we could do with this. This right here could also be thought of as W, but notice I drew it a little bit differently in terms of just understanding what that would be, because W is pounds, and the change of tension, let's see. Actually, all of a sudden when I'm looking at that, I'm thinking that doesn't make a lot of sense. Let's leave that for a second, because that's actually kind of bugging me all of a sudden, even though I thought I understood it. What that really does is, because there's two ways of like talking about the weight of a chain. One of them is, how much does that chain weigh? 900 pounds. The other one is how much does it weigh in pounds per foot, which is kind of a better thing to know, because if you're told, oh, that type of chain right there, that weighs 6 pounds a foot. I mean, that's kind of cool to know, because then you can know the weight of any chain you want. It's like, how long is that chain? Oh, 8 feet. Okay, well, if it's 10 pounds per foot, that means it's 80 pounds. That's what that little W represents. What's bothering me, just because I'll kind of speak this out loud, is if W is pounds and T is tension, isn't tension also measured in pounds? I'm looking at that thinking, why would that be pounds per feet? All of a sudden I'm looking at that thinking I don't really feel too good about that. The units of that are bugging me. Cool. What about DT? Let's just see, where are we at then if I write it this way? I guess we would say, so where are we? We are at D squared. I'm just going to write this on the left side of the equal sign since that's kind of where you usually see it. And now I'm replacing dw dx with little w. It's still over the top of h, but then that's multiplied by dt dx. Algebraically, do you agree with that statement? Even though maybe we're not super happy with that w. But let's consider now this dt dx. Would you agree with this? In our picture up above, if this was t, then I could also talk about it being a little tiny amount of t. That's all dt means. It's a tiny amount of t. And if that's the case, isn't this a tiny amount of x and isn't this a tiny amount of y? So it's no different than it was before. It's just those are lengths. But remember, that's actually curving. And so, you know, this have to be tiny if you think about it. So if that's the case, based on Pythagorean theorem, would you agree that dt would be, according to Pythagorean theorem, wouldn't it be the square root of dx squared plus dy squared? According to Pythagorean theorem. So then I guess I could say that d squared dx equals times the square root of dx squared plus dy squared over dx. Now notice, do you see why we like that? Why do we like that? Why are we glad there's no more dt anymore?
Because we're all in X and Y land.
Yeah, we're in X and Y land. That's exactly right. And W and H are constants. And we're actually almost done. Now, would you agree that I could put that differently? I could include that dx on the bottom inside the square root if I squared it so that it could go in there. Would you agree that that's true? And this is something I showed you before because we used this to find arc length back in calculus earlier on when we were doing integration in Calc 2. This is a formula we built in calculus because we said, you know, arc length is how long is that line right there? Well, it's curving. So how are we going to find it if it's curved? Well, let's just make it really tiny because if it's really tiny, it's straight. And then let's add all those up. And so we created the same type of formula. Well, if you notice, then doesn't that become dx squared over dx squared is 1 and dy squared over dx squared is dy over dx squared? We're there. So, whoa, what am I doing? What color do we need? Black. Let's go F. So that means dy dx squared equals different w, the square root of 1 plus dy dx. In other words, the derivative. And notice that does not say the derivative twice. Do you understand that? That does not say the derivative twice. That is dy over dx and then squared. That is one derivative, but square the answer to that derivative. My pen just died. So I'm going to put a 2 up there in a second when my pen wakes up. Well, isn't that what we started with? Isn't that the equation I just kind of gave you in this problem? The pen is alive. Except that, we just make the kind of the neat conclusion that although these numbers actually mean things, we're just going to call this some other constant name A. And the only reason we're doing that is because it's kind of cool that that actually shows up on the graph. I mean, isn't that kind of neat? But it's actually the weight of the cable in pounds per foot divided by the tension that you would feel if you were holding the left side over there. I mean, that's what that A actually represents in terms of physics or engineering. But in terms of algebra, it's the y-intercept. And so the question is, the thing I want you to see that I think is rather beautiful is this is the only access to try to figure out what's going on with this shape, what's happening with it. And so engineers, mathematicians, physicists said, well, we know the forces have to balance here. And if we do some algebra to try to get rid of the letters we don't really want in this problem and try to get it down to, like Connor said, X and Y land, if we can get it all down to that level, then maybe we can solve it. And then we were, if you will, disappointed to discover, wow, that's a second derivative. That's a second order differential equation. Notice it's not linear because technically there's a derivative right here. That's not linear. And then there's a square root. So this is a second order differential equation, but it's not linear. The question is now for you, again, you don't need to know any of what I just showed you. I just show you that because maybe after you get this, you'll want to go back and look at it and make a little of your own sense of it. Your goal then is quite simply just to take that shape. And notice I wrote it a little differently. Like, it is important to understand when you're trying to solve this thing that you need to recognize that's really, dy dx, not squared, but actually two derivatives, whereas this is actually dy dx actually squared. And so this is weirder. Like, this does not look like the other second order differential equations we've been solving sterilely lately that look like kind of the quadratic formula, that sort of a look. It doesn't look like that. Like, you're gonna have to get kind of creative here. That to get rid of derivatives, you have to take integrals. But remember, we're searching for some y equation and we don't know what it looks like. Well, yeah, we do. It looks like this. So, when it comes to taking the derivative of y, you have to think, I can't take the derivative of y because I don't know what that is yet. Again, we're trying to put ourselves in the position of the first people that ever figured this out. And I hope you can kind of enjoy that feeling for a second, like to be able to create this equation and say, okay, wow, that's cool. That's the only access we have to this problem, is an equation that came with derivatives. And so, man, is there some equation that would actually make this equal sign true? What equation could I take a second derivative of, get some answer, and then over on the other side, take a first derivative, square it, add it to 1, square root it, and multiply it by 1/a, and those would actually be equal? What kind of an equation would do that? I'm certainly not going to guess it. So it is not easy, but it is within your ability to play around with that. But just think about algebra that like there's a square root. Can't you square both sides? There's 1/a. Couldn't I multiply both sides by a? There's stuff that you can do algebraically to this, but it's just important to recognize y is an equation and I don't know what it is. So I got to be careful. I can't find y prime. I can't find the derivative of something when I don't know what it is.
Can I give a conjecture on what to do for that?
Oh, that's a good question. I want to say not yet.
Okay, that's fine.
I'd like as many people, because your conjecture, and in the end, I do want you all to kind of put your heads together, but spend a little time alone and see what you can do under your own power. But I love the word conjecture, like try something and see if it kind of goes somewhere. Based on the last problem I did for you guys yesterday, don't be deterred easily that if what you tried is a dead end. There's actually more than one way to get this to work. And you have two basic methods. You have Laplace transforms. So I could just say, well, I'll take the Laplace transform of both sides right now, or maybe I'll square both sides and I'll take the Laplace. I don't know. Or, the guessing technique. That's what we did earlier for y double primes. And so could I mess around with this and then just kind of guess. I mean, you might say, well, guessing doesn't appear to be going to work so good because I don't know if I'd ever guess that. But remember, there are answers here. Like, isn't that what we got for guesses before was answers? So maybe that's not so surprising. And so, that's where these two answers come from, is one taking the old approach and two taking the Laplace transform approach. And I want to see if you can actually get both of these. So that is what you owe me. But again, I just want to highlight, I really would like everybody to get this, but that does not mean you go home by yourself and either just think it up out of your head or cheat in some form and, find somebody online who already did it and just copy their stuff down. I'm not going to know the difference if you do that. But man, what a shame, to get this under your own power is so cool. Why would you waste that chance? I'd rather give you a little hint, so that you can get it as much under your own power as you possibly can. So you have a number of days, and please take me up on that, because I want to see you be smart. I want to see you walk down the road and actually kind of feel like you own that shape, as opposed to, well, I don't know much about it. I just cheated my way through that class. Okay. So we have an hour for you to do whatever you want. If somebody asks a question and you don't care about that question, then just ignore the discussion and work on whatever you're working on. But obviously you can ask me questions about this project. Given that I want other people to think about this, if you have a project related thought, we'll probably jump into a breakout room, just so that you don't give away something if you happen to be one of the first people to come up with a good idea.